When simulating Verilog and SystemVerilog, there are several tools that you can choose from, and the most popular SystemVerilog simulators, consisting of Synopsys VCS, Siemens Questosim, and Cadence Exilium, are often referred to as the Big Three for their high level of compliance with the IEEE 1364 and 1800 standards. However, a license for one of these tools can cost thousands of dollars, making them completely infeasible for many people. But fortunately, the next most popular SystemVerilog simulator is Verilator, and Verilator is free and open source, and often gives more helpful warnings and runs faster simulations than any of the big three. Now, this sounds great, but Verilator isn't actually fully IEEE compliant. For example, it does not yet support UVM elaboration, nor does it support 4-state values. But compared to the next most popular open source simulator, Icarus, Verilator has far superior support and features. So in this video, I wanted to quickly show you how to get started using Verilator and its many features. The best way to install Verilator is through the OSS CAD Suite GitHub repository. Every day, this repository recompiles and releases the latest versions of dozens of the most popular Verilog tools. This is much better than using the famously out-of-date releases found in package managers, such as apt and brew. To download the OSS CAD Suite binaries, simply go into the Releases tab and copy the download link for whichever operating system and architecture matches your machine. Then, in your terminal, type wget, then paste in the download link. After waiting for it to download, simply extract the tar file with tar-xzf, then move the extracted OSS CAD Suite directory wherever you would like. I like to put it in a utils directory. You can also add the OSS CAD Suite /bin directory to your path environment variable for easy access. You can now run Verilator ---- version to ensure that you did things correctly. However, if the OSS CAD Suite Verilator release happens to be broken, then you can just choose to build Verilator from source according to steps in the Verilator documentation. Great, and now that Verilator is installed, I can show you a basic example of how to get it running. So first I will create a module called test that just runs hello, and then I will also create a basic test bench that just instantiates this module and then exits after one time step. All right, and next we will compile our design using Verilator. To do this, you just type in Verilator ---- binary to create an executable, and then we can put in our source file names, so test.sv and tb.sv, and then we need to include --top and then tb, because in this case the top level module is tb. And then it compiles, and then now we can run the executable that was generated by /obdir vtb. And you can see that it prints out hello, just like we would expect. And also, you may notice that Verilator made several calls to G++. And this is because all that Verilator actually does is just converts or verilates Verilog code into C++. And by including ---- binary, G++ is automatically run after Verilation to create our binary. And if we go into the obdir directory, you can actually see all of these generated C++ files. And this can be an incredibly useful aspect of Verilator, because now you could potentially interface with third-party C++ libraries to add GUIs, unit test frameworks, or really anything you want. So it's really powerful, but also optional. Let me now show you one of the most defining characteristics of Verilator, which is its super thorough warning system. If you ever use a well-known bad practice or unsynthesizable Verilog construct, then Verilator will most likely report an extremely clear warning message so you can easily go in and fix your code. And to show this, I'll just add a simple always con block to the test module, and I'll drive the inputs in the test bench. And next we can rerun Verilator, and I'll add the source files again. But compiling the design kind of takes a while. I just wanted to check if the code I've written will give any errors. But fortunately, instead of creating an executable with ---- binary, I can just use ---- only, and then I will also do -wall to show all warnings. And oh, oops, I forgot to add ---- timing to allow the use of delay constructs. And now we can see that the code that I wrote has several warnings. And it looks like I had two issues with my always com block. One was that I used a non-blocking assignment, and the other was that I accidentally inferred a latch. So let me just fix those issues really quick. However, my test bench is still getting an error because I'm not actually using the test output signal. But I never really intended to use this signal because I'm just hoping to look at it in my waveform viewer, not actually touch it in the simulation. But fortunately, I can disable any warning I want, including this unused signal warning, by either adding a Verilator lint off directive in a comment, or by disabling the warning through command line arguments, or by creating a Verilator configuration file. And you can just pick your favorite option for your specific use case, as all three of these options are basically equally popular. But our Verilator command is getting pretty long now, so let's now reorganize our build command arguments into a separate file commonly referred to as a file list. And I can now run this file through verilator-f verilator.f. And you can see that the behavior is exactly the same. Although I like to keep the Verilator mode outside of the file list, such as --lint only and --binary. That way I can use the same file list file across different types of runs. And there are tons of super useful arguments that Verilator supports, so I highly recommend looking through the documentation if you have any questions. But let me now paste in several of my favorite options that I highly recommend adding to all your Verilator runs. The first enables full warning reporting. The next allows Verilation to complete even if a warning is encountered. The next enables multithreading. The next enables SystemVerilog assertions. The next compresses the waveform output. The next prints structs as human readable format. The next treats assignments to unknown values as random integers instead. And the final customizes the initial values of all signals. And the reason for these final two arguments is due to the largest issue with Verilator, that Verilator simulations cannot yet handle unknown or high impedance values, also known as four-state values. And to quickly demonstrate this, I created a test bench that simply assigns all four possible states. And here are the waveform outputs generated by VCS and Icarus, which are tools that properly support four-state values. Versus here is Verilator's waveforms for each of the possible runtime options for Verilator rand reset. And as you can see, Verilator incorrectly flattens all four-state values into two-state integers. Now, there is a semi-active GitHub issue discussing adding four-state value support, so maybe within the next few years, unknown values will be fully supported, but for now, you'll just have to deal with handling them through command line arguments. And similarly, UVM elaboration is currently being worked on by the Antmicro team, and I suspect that it will be in a highly usable state by 2025. And of course, that date will be even closer if you, the viewer, help contribute to Verilator's codebase. Verilator is maintained by Wilson Snyder, who is extremely kind, and he does a fantastic job of keeping the codebase very organized, even as Verilator continues to get constant updates. So if you have any feature requests or bug reports, feel free to create an issue, and Wilson will likely get back to you within just a few days. And that concludes this introduction to Verilator. Feel free to like, comment, and subscribe, and I'll see you in the next video.
And called Model Sim, and he's like, $5,000 or something like that. Like, well, I'm not doing that.